Welcome to today's problem walkthrough. In this session, we'll be tackling problem number 122, best time to buy and sell stock 2. This is a classic dynamic programming problem that challenges us to maximize profit across multiple stock trades. Let's dive in and explore the approaches to solve this efficiently. The problem, best time to buy and sell stock 2, asks us to determine the maximum profit we can achieve by buying and selling a stock over a given period. You are provided with an array called prices, where each element represents the stock price on a specific day. On any given day, you can choose to either buy the stock, sell the stock if you already own it, or do nothing. However, there is a key condition: you can only hold at most one share of the stock at any time. This means if you already own the stock, you must sell it before buying again. The challenge is to maximize your total profit by making as many transactions as needed, where a transaction is defined as buying one share and then selling it later. The input is an array of stock prices, and the output is an integer representing the maximum profit you can achieve through optimal transactions. To better understand the problem, let's look at an example. Suppose the input array of prices is 7, 1, 5, 3, 6, 4. Here's how you can maximize your profit. On day 2, when the price is 1, you buy the stock. Then, on day 3, when the price rises to 5, you sell it, making a profit of 4. Next, on day 4, when the price dips to 3, you buy again, and on day 5, when the price reaches 6, you sell, earning another profit of 3. Adding these profits together gives a total profit of 7. This demonstrates how multiple transactions can be used to achieve the maximum possible profit. Now, consider a second example where the prices are 1, 2, 3, 4, 5. In this case, the prices are strictly increasing. The optimal strategy would be to buy on day 1, when the price is 1, and sell on day 5, when the price is 5, resulting in a profit of 4. Alternatively, you could make multiple transactions, buying and selling each day as the price increases. For instance, buy on day 1, sell on day 2, buy again on day 2, sell on day 3, and so on. Both approaches yield the same total profit of 4, showing that the solution is flexible in terms of how transactions are structured. Finally, let's examine an example where the prices are 7, 6, 4, 3, 1. Here, the prices are in a non-increasing order, meaning they continuously drop over time. In such a case, no profitable transactions can be made because the stock price never rises after you buy it. Therefore, the maximum profit is 0. Additionally, we need to consider edge cases. If the array contains only one price, it's impossible to make any transactions, so the profit is 0. Similarly, if all prices decrease over time, the profit remains 0. On the other hand, if the prices continuously increase, the best strategy is to buy at the lowest price and sell at the highest price, or alternatively, use multiple transactions to achieve the same result. To solve this problem, we first consider the brute force approach. The idea here is to simulate every possible pair of buy and sell days in the array. For each day, we assume a buy, and then for every following day, we simulate a sell. By summing up the profits from all these transactions, we can compute the maximum possible profit. However, this approach involves nested loops, which means the time complexity is O(n squared). While it's straightforward to understand, this method becomes impractical for larger arrays due to its inefficiency. Now, turning to the greedy approach, we take advantage of an important observation. To maximize profit, all we need to do is capture every positive price difference between consecutive days. Instead of explicitly identifying buy and sell days, we simply iterate through the array and add the profit whenever the price of the next day is higher than the current day. This method is both efficient and intuitive, as it reduces the problem to summing up these positive differences, resulting in a time complexity of O(n). Another possible strategy is using dynamic programming. This approach involves maintaining two states for each day: the maximum profit when holding a stock and the maximum profit when not holding a stock. By using recurrence relations, we can determine the transitions between these states depending on whether we buy, sell, or skip on a given day. While this approach is theoretically optimal with a time complexity of O(n) and space complexity of O(1), it is more complex to implement and less intuitive for this particular problem. Dynamic programming is generally better suited for more constrained scenarios, like when there are limits on the number of transactions. Ultimately, the greedy approach stands out as the chosen strategy due to its simplicity, efficiency, and clear logic. By recognizing that capturing all positive price differences between consecutive days achieves the same result as explicitly tracking buy and sell days, the greedy method offers an elegant solution. Compared to the brute force approach, which is inefficient, and dynamic programming, which is overcomplicated for this problem, the greedy solution provides the best balance of clarity and performance, making it the ideal choice here. In this problem, the objective is to determine the maximum profit that can be achieved by buying and selling a stock on different days. The key restriction is that you must sell a stock before you can buy it again, but you are allowed to make as many transactions as you like. To solve this, we first consider the brute force approach. Here, we initialize a variable max_profit to 0, which will store the accumulated profit from all valid transactions. Then we use two nested loops. The outer loop iterates over all possible days to buy the stock, while the inner loop considers all subsequent days as potential sell days. For each pair of buy and sell days, we calculate the profit as the difference between the sell price and the buy price. If this profit is positive, we add it to max_profit. After all iterations, max_profit will contain the total profit from all profitable transactions. However, this approach has a time complexity of n², which can be inefficient for larger inputs. To improve this, we can observe that the problem is essentially about capturing upward trends in stock prices, which allows us to simplify the algorithm significantly. The optimized approach begins by initializing max_profit to 0. Instead of using nested loops, we make a single pass through the array of prices, starting from the second day. On each day, we compare the stock price with the previous day's price. Whenever the current day's price is higher, it means there's an upward trend, and we calculate the profit as the difference between these two prices. This profit is then added to max_profit. By summing up all such upward price differences, we ensure that we capture all possible profits without explicitly tracking individual transactions. This method leverages a greedy strategy, focusing only on the segments where the stock price increases. Some key insights include handling edge cases. If the input array is empty or contains only one price, no transactions can be made, so the profit is 0. Similarly, if all prices are in descending order, there are no upward trends, and the profit remains 0. The algorithm uses the input array to track prices and a single variable to accumulate profit, ensuring minimal space usage. The optimized algorithm is highly efficient. Its time complexity is n, because we make just one pass through the array, and its space complexity is 1, since no additional data structures are used. To illustrate this, let's walk through an example. Consider the input prices as 7, 1, 5, 3, 6, 4. On day 1, the price rises from 1 to 5, giving a profit of 4. On day 3, the price rises from 3 to 6, adding another profit of 3. Summing these, the total profit is 7. In contrast, for an input like 7, 6, 4, 3, 1, where prices only decrease, there are no upward trends, so the profit is 0. The corresponding pseudocode for the optimized algorithm is straightforward: iterate through the array, adding the difference between consecutive prices whenever the later price is greater. This simplicity highlights the effectiveness of the greedy strategy in solving the problem. The optimized approach offers several key benefits. It simplifies the solution by focusing directly on upward price trends, avoiding the complexity of trying all possible buy-sell pairs. This results in a significant efficiency boost, reducing the time complexity from n² to n. Additionally, the approach is easy to understand and implement, making it suitable even for large input sizes where performance is critical. By leveraging the greedy strategy to sum up all profitable segments in a single pass, the algorithm ensures that no potential profit is missed. In conclusion, this method is both elegant and practical, providing an optimal solution to the problem while maintaining clarity and efficiency. This makes it a robust approach for maximizing stock trading profits within the given constraints. This code solves the LeetCode problem number 122, best time to buy and sell stock 2, by efficiently calculating the maximum profit from a sequence of stock prices. The problem allows multiple transactions, but mandates that each buy must precede its corresponding sell. The goal is to maximize profit by identifying opportunities to buy low and sell high across the given price array. Here's how the solution works. 1. Initialization. We start by initializing a variable max_profit to 0. This variable will store the cumulative profit as we traverse the price array. 2. Iterate through prices. Using a for loop, we iterate through the prices list starting from the second day, I equals 1. This allows us to compare each day's price with the previous day's price. 3. Profit calculation. On each iteration, we check if the current day's price, prices, I, is higher than the previous day's price, prices, I'd 1. If it is, we calculate the profit from buying at the previous day's price and selling at the current day's price. This profit is added to max_profit. For no transaction on price drops, if the price drops or remains the same on a particular day, we skip that day since no profitable transaction can be made. 5. Return the result. After completing the loop, the total max_profit accumulated over all profitable transactions is returned as the result. Key insights. Greedy approach. The algorithm takes a greedy approach by adding all upward price differences. This ensures that every profitable opportunity is captured without explicitly modeling each buy-sell transaction. Efficiency. The solution runs in O(n) time, where n is the length of the price array. This is achieved by using a single loop and constant space, making it highly efficient. Edge cases. The code handles edge cases such as an empty prices list or a single-day price list. Output will be 0 since no transactions are possible. A monotonically decreasing price array. Output will also be 0 as no profit can be made. This straightforward and efficient solution meets the problem's requirements by leveraging the greedy method to maximize profit in linear time. This is the Java implementation for LeetCode problem number 122, best time to buy and sell stock 2. The logic mirrors the Python solution, where we calculate the total profit by summing up the differences between consecutive prices whenever the price increases. Key differences include Java's explicit array type declarations and the class structure. The max profit method takes an array of integers as input and returns the maximum profit as an integer. The implementation ensures efficient iteration with O(n) time complexity. Here, we start with an example where the prices are steadily increasing each day. The input array is 1, 2, 3, 4, 5. First, we initialize max_profit to 0. Then, we iterate through the prices starting from the second day. On day 2, we see that prices 1 is 2 and prices 0 is 1. Since 2 is greater than 1, we calculate the profit as 2 1 equals 1 and add it to max_profit, making max_profit equal to 1. On day 3, prices 2 is 3 and prices 1 is 2. Again, 3 is greater than 2, so we calculate the profit as 3 2 equals 1 and add it to max_profit, resulting in max_profit equals 2. On day 4, prices 3 is 4 and prices 2 is 3. The difference, for 3 equals 1, is added to max_profit, making it 3. Finally, on day 5, prices 4 is 5 and prices 3 is 4. Since 5 is greater than 4, we calculate 4 equals 1 and add it to max_profit, bringing the total to 4. At the end of the loop, the total max_profit is 4, which is the output for this example. Now, let's look at an example with mixed price movements, where the input is 7, 1, 5, 3, 6, 4. As before, we initialize max_profit to 0 and start iterating from the second day. On day 2, prices 1 is 1 and prices 0 is 7. Since 1 is less than 7, no profit is added, and max_profit remains 0. On day 3, prices 2 is 5 and prices 1 is 1. Here, 5 is greater than 1, so we calculate the profit as 5 1 equals 4 and add it to max_profit, making it 4. On day 4, prices 3 is 3 and prices 2 is 5. Since 3 is less than 5, no profit is added, and max_profit remains 4. On day 5, prices 4 is 6 and prices 3 is 3. Since 6 is greater than 3, we calculate the profit as 6 3 equals 3 and add it to max_profit, which now becomes 7. Finally, on day 6, prices 5 is 4 and prices 4 is 6. Since 4 is less than 6, no profit is added, leaving max_profit at 7. At the end of the loop, the total max underscore profit is 7, which is the output for this example. Lastly, let's examine an example where the prices are consistently decreasing, with the input 5, 4, 3, 2, 1. We initialize max underscore profit to 0 and start iterating from the second day. On day 2, prices 1 is 4 and prices 0 is 5. Since 4 is less than 5, no profit is added, and max underscore profit remains 0. On day 3, prices 2 is 3 and prices 1 is 4. Again, since 3 is less than 4, no profit is added, and max underscore profit stays at 0. On day 4, prices 3 is 2 and prices 2 is 3. Since 2 is less than 3, no profit is added, and max underscore profit remains 0. Finally, on day 5, prices 4 is 1 and prices 3 is 2. Since 1 is less than 2, no profit is added, leaving max underscore profit at 0. At the end of the loop, the total max underscore profit is 0, which is the output for this example. The time complexity of this solution can be broken down based on the operations within the loop. The algorithm uses a single for loop that iterates through the prices list, starting from the second element and going to the last. If we let n represent the size of the prices list, the loop executes in 1 iterations in the worst case. Within each iteration, a constant time comparison is made to check if the current price is greater than the previous price. If the condition is true, a subtraction and an addition operation are performed, both of which also take constant time. Since these operations are O(1), the total time complexity is determined by the number of iterations, which is proportional to n. Multiplying the number of iterations, O(n1), by the constant time operations inside the loop, O(1), gives us an overall time complexity of O(n). This means the algorithm scales linearly with the size of the input list. Now turning to space complexity, the algorithm is highly efficient in this regard. It uses a single variable, max underscore profit, to track the accumulated profit. This variable requires a fixed amount of memory, regardless of the size of the input. Furthermore, no additional data structures are used, and the input list prices is only accessed in a read-only manner. Since the algorithm does not allocate any extra memory that grows with the input size, the space complexity is constant. In other words, the space complexity of this solution is O(1). Next, let's analyze the time and space complexity for the best, average, and worst-case scenarios. In the best case, the prices are in non-increasing order, such as 5, 4, 3, 2, 1. Here, the condition prices I1 is never true, and the loop only performs comparisons for n1 iterations without any profit calculations. The time complexity remains O(n), and the space complexity is O(1). In the average case, the loop still executes n1 iterations, but the condition is true for some subset of iterations, leading to a mix of comparisons and profit calculations. Again, time complexity remains O(n), and space complexity stays at O(1). In the worst case, when prices are strictly increasing, such as 1, 2, 3, 4, 5, the condition is true for every iteration, resulting in profit being calculated in all n1 iterations. The time complexity is still O(n), and space complexity remains O(1). Compared to a brute force approach, which would involve generating all possible buy-sell pairs and calculating profits for each, resulting in a time complexity of O(n², this optimized approach avoids unnecessary calculations by summing profits for increasing sequences in a single pass, reducing the time complexity to O(n), while maintaining the same O(1) space complexity. Finally, let's provide a mathematical justification for the big O analysis. The time complexity is O(n), because the loop executes n1 iterations in the worst case, and each iteration involves a constant number of operations, including comparisons and occasional additions. With no nested loops or recursive calls, the runtime grows linearly with the input size. For space complexity, the algorithm uses only a fixed amount of extra memory, specifically the variable max underscore profit, and does not require any additional data structures or allocations. This results in a constant space complexity of O(1). The absence of nested computations and the efficient use of memory confirm that the algorithm achieves linear time complexity and constant space complexity, making it optimal for this problem. When solving this problem, there are several pitfalls to watch out for. First, incorrect nested loops are a frequent issue in brute force approaches. Iterating over all pairs of days without ensuring that the sell day comes after the buy day violates the problem's constraints and will result in invalid outputs. The solution here is to start the inner loop at I+1, which ensures the sell day is always after the buy day. Next, edge cases are another common source of errors. For example, if the input list is empty or has only one element, it's impossible to make a profit, and failing to handle these cases can lead to runtime errors. A simple check at the start of the function to return 0 for such cases can prevent this. Another mistake involves misunderstanding how to calculate profit. Some might try subtracting prices for all pairs of days without focusing on maximizing the profit. Instead, it's crucial to track and update the maximum profit dynamically as you iterate. Lastly, inefficient use of space can arise if you store intermediate results unnecessarily in an additional data structure. You can avoid this by using a single variable to maintain the running maximum profit, which ensures an O(1) space complexity solution. Overcomplicating the optimized solution is another common challenge. Some people try to track multiple buy and sell days simultaneously, which can result in overly complex logic and errors. Instead, it's better to stick to the simplest one-pass solution, where you focus on tracking the minimum price so far and calculating the potential profit for each day. This not only keeps the logic clear but also ensures efficiency. In interviews, recognizing the key pattern of this problem is essential. It revolves around finding the maximum difference between two numbers, ensuring that the smaller number appears before the larger one. Being able to identify this pattern quickly can give you an edge. The optimal solution involves maintaining the minimum price as you iterate through the list, calculating the profit for each day, and updating the maximum profit if needed. This has a time complexity of O(n), and is often what interviewers expect you to implement. Don't forget to address edge cases as well. For example, discuss scenarios like an empty input, a single element array, or a strictly decreasing price list, where no profit is possible. Finally, interviewers might also ask about variations of the problem, such as allowing multiple transactions or placing a limit on the number of transactions. Make sure you're ready to adapt your approach if these follow-up questions come up. This problem is closely related to several other stock buying problems on LeetCode. For example, in Best Time to Buy and Sell Stock 2, multiple transactions are allowed, which adds a layer of complexity. In Best Time to Buy and Sell Stock 3, at most 2 transactions are allowed, requiring a more sophisticated approach. Best Time to Buy and Sell Stock with Cooldown introduces a restriction where you must wait for a cooldown period after each sell, adding another constraint. Even the maximum subarray problem shares a similar concept, as it also focuses on finding a maximum difference, though it applies to subarrays rather than stock prices. Now, when it comes to approaches and trade-offs, brute force is the simplest and most intuitive method, but it has a time complexity of O(n squared, making it impractical for large inputs. While it's useful for understanding the problem, it should be optimized during interviews. The one-pass solution, with a time complexity of O(n), is the most efficient and widely accepted approach. By tracking the minimum price and calculating profit in a single loop, it strikes the perfect balance between simplicity and performance. Lastly, there's the divide and conquer approach, which has a complexity of O(n log n). While it's an interesting method that splits the array into halves to find the maximum profit, it's rarely preferred over the one-pass solution due to its higher complexity. Great job making it to the end. To summarize, we tackled maximizing stock trading profits with various approaches, reviewed complexities, and discussed key takeaways. Remember to practice similar problems to strengthen your skills. Thank you for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!